Okay, students, I hope the screen is visible to all of you. Okay. Good morning to everyone present in the session and welcome back after your Diwali vacations. This is the very first lecture of data structures after your vacations, and we are going to continue with what we had paused in our session. So I'll revise a bit so that you can recall everything. Okay, and then we'll start with the portion ahead. See, in the last session, we were discussing your AVL trees. Okay, so I'm going to start with that only. We have seen till this rebalancing. Okay, till this case one RR rotation we have seen, but I'll quickly revise you the AVL trees. Okay. See, your AVL trees are what? Your self-balancing binary search tree. Okay, so when we talk about AVL trees, you have to keep in mind the properties of balancing trees, that is height balance trees, and the property of binary search tree. Okay, the mixture of two. So AVL tree is the self-balancing binary search tree. Okay, now when I talk about properties of binary search tree, we already know that the root node left portion from the root node, the left main subtree, okay, are the values which are less than your root node. Fine. And on the right subtree are the values which are greater than your root node. Okay, so that is the properties of binary search tree. And what about self balancing? See, we also know that we have to calculate the balance factor at each and every node. Okay, so once the insertion is done, you are going to check whether the height balancing, okay, or say the balance factor is within the range. What was our range? -1, 0 and 1. If the balancing factor is out of these three, then you need rotations. Okay, so this is the properties which you need to keep in mind while you are dealing with your AVL trees. Balance factor should not be greater than -1, should not be other than -1, 0 or 1. Okay, and it should consider or it should satisfy the properties of binary search tree. Okay, if anything like this is not there, if it is not in within the range, or if it is not satisfying the properties of binary search tree, okay, then you need rotations. Fine. So that is what in short you can say about this property. Whatever I have said, it is all described again in the written form here, that in an AVL tree, heights of two child subtrees of any node differs by at most 1. So in easier manner, if you want to remember, the range should be -1, 0 or 1. इसके अलावा और कोई नहीं चलेगा. ठीक है, बैलेंस फैक्टर में the value should be -1, 0 or 1. If at any time they differ by more than 1, okay, then you need rebalancing to restore the property. Insertions and deletions require, may or may not require, okay, the tree to be rebalanced by one or more rotations. Okay, so the concept again, they are your height balance binary search tree, balance factor of the node. How you are going to calculate that? Height of your left subtree minus the height of your right subtree. Okay, so and you have to remember that you have to calculate balance factor at each and every node after each and every deletion or insertion. Okay, whichever operation you are doing, after each operation you have to calculate the balance factor at each and every node. Everybody with me till here? Yes or no? Okay. So see again, for every node, height of left and right subtree can differ by no more than 1. Okay. In simple terms, it should be either -1, it should be 0 or 1. No other value than these three. And you have to store the current heights, the balance factors at each and every nodes. We had seen this example. Okay, so I'm not repeating it again. The operations which we discussed were the search operation in your AVL tree, your insert, which will include the rotations. Okay, this is LL, that means left rotation. Then there is LR, that is left right rotation. Then it is RR, that is right rotation. And then it is RL, that is right left rotations. Okay, so when you are going and inserting any node in your AVL tree, you may require rotations. Okay, and what kind of rotations you may require? These four kinds. Out of these four kinds, you may require any one of them. Okay, then there are delete rotations. Okay, again delete rotations have these types: L0, R0, R1, R-1, L0, L1 and L-1, depending upon what kind of balancing you need. Okay, the search operation we have covered. It is, you don't need to modify your tree. Simply you can apply the same search operation as you are doing in your binary search tree. Okay, so there are no special provisions which are to be required. Fine, the easiest operation in your AVL tree. Then we came into your insert. That means rebalancing. See, once you insert any node either on the left subtree or the right subtree, obviously the balancing factor at each and every node will differ. Okay, so in that case you'll need rebalancing. So again, an AVL tree whose root has 0 balance factor cannot be unbalanced. Okay, if the root node is having 0 balance factor, that means it is a perfectly balanced AVL tree. Okay, so you don't need any rebalancing there. Fine. Okay, if you add a node to such kind of a subtree, then obviously it is going to increase the height of a subtree at most by 1, either on the right side or the left side, depending upon the value. Fine. Therefore, you are going to need the balance factor. Therefore, the balance factor of the tree will change to +1 or -1, thus keeping your tree balanced. Okay. Rotation is not going to be required because it is within the range +1, 0 and -1. So you won't need rotation. But after this, again you are going and inserting. Okay. Then you are going to need obviously any 4 of the cases. Okay, and in which case 1 we have already discussed, that is your RR rotation. Now what is your RR rotation? Let's see it again with an example. Suppose ABC is the string, okay, or say ABC are the elements from which I have to create an AVL tree. Okay, so obviously the first one is going to be my root node. So the first element is A. So I inserted A. Balance factor I am calculating. No children are here. Okay, so balance factor is 0. In the next step, I am adding B. Okay, now B is greater than A. How I am taking this? Because in your alphabetical sequence from 1 to 26 letters, B is the second letter. Okay, A is the first letter, B is the second letter. So B is greater than A. Okay, in those terms, I am taking B as greater than A. Okay, so B will be on the right side because it is greater than A. Again, go and calculate the balance factor. What is the balance factor at B? 0, because B does not have any children. Okay, so no left minus right heights. Fine. So B is 0. Now here at A, balance factor changes. Okay, it changes to -1 because left side it is 0, right side it is 1, and 0 minus 1 is -1. Okay, so A is -1 here. Alright. Now go and again insert another element. Fine, because we don't need rotation here, it is within the range. So again now go for the next insertion. Now you are adding C. C is greater than A, it is also greater than B. So it will be on the right side of B. Okay, if you can see here, just a minute. Okay, C is here, C, at this point, at the right side. Okay, now go and calculate again the balance factor, because what I said, every time you do an insertion, every time you have to calculate the balance factor at each and every node. Okay, so balance factor at C will be 0 for the obvious reasons, because it does not have any children, right or left. Balance factor at B, it will change. Initially it was 0. Okay, after addition of C, after insertion of C, left of B we don't have anything. Okay, you do not have any children on the left side, so that height is 0, and 0 minus 1, so balance factor at B is -1. Okay, now at A, it does not have any left child. Okay, so height at left is what? 0. But what is the height on right side? 1 and 2. Okay, so 0 minus 2, so balance factor is -2. Now it went out of range. Okay, our range was -1, 0 and 1, but here we are getting -2. And why we are getting -2? Because there were two right insertions. Okay, two right insertions. So this case is what? This case is of RR rotation. Okay, so in that case what you will do? You will rotate first. This case is of RR rotation. Okay, and in that case, to resolve this, what you are going to do? You are going to rotate your median value. Okay, your median value out of this 3, which is the median value? Your B. Okay, this B is your median value. This is the easiest trick. Okay, if you don't remember that exactly from which node you are going to rotate, then keep in mind, okay students, that you have to rotate from the median value. So your median value will become your parent node. Median value out of this 3 is B. Okay, so you'll rotate from here, and it is RR rotation. Okay, so you're going to rotate on the left side. Okay, step 1, select your median value out of 3. Step 2, rotate on left side, because it is RR rotation. Okay, so rotate on left side. So once you rotate it on left side, your median value is pulled up. If you see in a mechanism, okay, this median value B is pulled up. So automatically when you rotate it, this A is going to rotate on left. Okay, so since this A came on the left side, okay, C value comes on the right side. Okay, you pulled that up. From this line you pulled this median value up. Okay, so does this satisfy my condition? Let's see. At node value A, what is the balance factor? 0. Okay, done. At node value C, what is the balance factor? 0. Okay, no issues here also. At node value B, what is the balance factor? 1 minus 1, so 0. Okay, so one property of height balancing agreed. Now look at binary search tree property. Root node is what? B. On the left side I have A. A is less than B? Yes. On the right side of B I have C. C is greater than B? Yes. So property is satisfied. So now I can say that this whole thing, this whole tree which I got here right now, okay, I have satisfied the properties of AVL tree. Thus I can say that this particular tree is my AVL tree. Everybody got it? With me till here everyone? Any doubt? Any doubt in this case?
मैम
Yes,
ए
please.
-1 और C+1 नहीं होना चाहिए?
नहीं, A-1 नहीं होगा क्योंकि A के कोई चाइल्ड नहीं है ना डियर यहाँ पे। Every time you are doing the rotation, you are going to newly calculate your balance factor. You are not going to calculate on basis of this. Okay? जब भी रोटेशन करोगे या तो जब भी इंसर्शन करोगे तो हर एक नोड के पास अगेन आप उसके बैलेंस फैक्टर चेक करोगे। बैलेंस फैक्टर के लिए हमारे पास क्या फॉर्मूला है कि हाइट ऑफ लेफ्ट चाइल्ड माइनस हाइट ऑफ राइट चाइल्ड। अभी ए और सी के पास तो चिल्ड्रन ही नहीं है, तो वहां पे तो जीरो ही हो गया ना, जीरो माइनस जीरो, सो दैट इज जीरो। गॉट इट विद्धि? क्लियर?
यस मैम।
ओके, एनीवन एल्स विद एनी डाउट और इज इट क्लियर? Students, this case is clear with all of you, yes or no? Rest of the students.
It's clear, ma'am.
Okay. Then we are moving forward to our case number 2. Okay. Your case 2 is your LL rotation. Okay. Your case 2 is left rotation. Again, there is a string of elements given to you. Suppose those elements are C, B, and A. Okay. C, B, and A. So apply the same rule. Go and insert the first element. So you inserted C. Calculate the balance factor. No children. So balance factor will be 0. Okay. So nothing to be done. Everything is fine. So go to the next insertion. Next insertion I have B. Now B is less than C. So obviously it is going to the left side because we are following the property of binary search tree. Again calculate the balance factor. For B, do I have any children of B? No. So balance factor is 0. For C, what will be the balance factor? Height of left child minus height of right child. But right child I don't have anything. Okay. So 1 minus 0. So balance factor at C, at node C will be 1. Okay. They are still within my range of my AV height balancing tree. Fine. So I don't need to do any rotation. Everything is fine. Now go for the third insertion. When you go for the third insertion, you come across element called A. Now we know that A is less than C. A is also less than B. Okay. So A is going to be placed on the left side. Go and calculate the balance factor again. At A does not have any children. So balance factor is 0. At B is having one left child, but it is not having any right child. Okay, so height on the right side is 0 for B. Height of the left side is 1. So 1 minus 0, balance factor 1. Okay, so still within the range, no issues. Now at C, go and calculate the height, the balance factor at C. C left side I have 1 and 2. Okay, height of left side. So it is 2, but I don't have anything on the right side. So that is 0 again. So 2 minus 0. So again it is 2. Now 2 is out of my range. So I need to rebalance this. There will be some kind of a rotation. Now why this balancing difference has occurred? Because I had two left insertions. So this case is of what? Left rotation. Okay. This is going to be the case of my LL rotation. Alright. Just wait. Okay, this is the case is going to be what of my left rotation. So again you are going to follow the same rule. Select the median value, okay, and this time you are going to rotate on right side. This is the case of LL rotation. Previously we saw the case of RR rotation. So if it was RR rotation, we were rebalancing by rotating it on left side. Here it is LL rotation. So with the help of rotation, how the rotation is going to occur? Rotation will be on the right side. Select the median value, pull that median value up. Okay, so it will be something like this. So the rotation which occurs, so basically what you are doing, this root value, this C root value is moved on the right side. Okay, if you observe this rotation, okay, this rotation if you observe, okay, you are pulling this B, that is the median value. Understand, here there are three values, so median value is easy to select. If it was 4, then you have to calculate the apt median value. Okay, though there won't be a case of any 4, but still median value you have to select. Fine, don't go in a mechanical way that okay बीच का value है तो उसको ले लो, ऐसे नहीं है. I am saying median value. Fine, so median value is B. Fine, so this C and A on left side, C on right side. Again go and calculate the balance factor. Balance factor at A is 0 because no children. Balance factor at C again is 0 because again C does not have any children. For B, height of left side 1, height of right side 1, 1 minus 1, it is 0. Balance factor 0. So you can say this is your ABL tree. Got it? LL rotation. See, these two are the easiest out of 4. Okay. RR rotation, rotate on left side. LL rotation, rotate on right side. The easiest of the 4 out of 4. Fine. Now we are going to the case number 3. Your case 3 is RL rotation, that is right left rotation. Suppose for example you are given this string, okay, this list of elements that A, C and B. So again you are going to repeat the same steps. Start inserting. Insert A. So balance factor at A. What is the balance factor at A? 0. Okay. So nothing to be done. It is my perfect AVL. Then next AC. Okay. What is AC? Again C is the greater than A. Alright. So again go and calculate the balance factor. At C it is going to be 0. Fine. See, always start calculating a balance factor from your leaf nodes. Alright. At C it is 0. At A I don't have any left side. Okay. No left side is there. Fine. So it is 0 and here it is 1. Okay. So 0 minus 1. What is it? Minus 1. Still within my range. I don't need any of my rotations. Alright. Now go next. Go and add. Now see, I have B. Okay, B is greater than A. So obviously it is going to go on the right side. But on right side I have element C. So I'm going to compare B with C. Okay, so B is less than C. So it is going to place on the left of C. Alright. Now go and calculate the balance factor. At B, what is the balance factor? 0. Okay. At C, what is the balance factor? 1 minus 0. Okay. So it is going to be 1. What is the balance factor at A? 0 minus 1 and 2. Okay. So it is going to be minus 2. So it went out of range. So I need rotation. But here, what is the case of my rotation? It is right, left. because first I inserted on the right side, then I went and inserted on the left side. Okay, so this case is of what? Right left rotation. All right. So again, what you have to do? You have to select the median value. All right. First of all, what you are going to do is you are going to simplify this. If you want to simplify this, I told you that the previous two cases are the easiest ones. Okay, LL rotation and RR rotation. So what you are going to do is you are going to try and make it in one of these conditions. Either you are going to make it as RR rotation or you are going to make it as an LL rotation. Okay, and in this case, in your LR rotation, you can easily make this tree into RR type. How? From this from this median value C, you are going to rotate on right side. Okay, see, again, once again I'm saying, you identified that this is RL rotation case. Okay, here it is -2. Okay, and you just saw that why this imbalancing is happening, because there was one right insertion and then there was one left insertion. All right, so the case becomes of RL rotation. Now what you have to make, in order to simplify this, in order to rebalance this, you have to simplify this whole tree. And in the simplification process, you have to convert this first of all into RR or LL rotation. Okay, because this is the case of RL rotation, you can easily convert this given problem into RR rotation first. Okay, so you are simplifying your problem from complex to a simple problem. Okay, so in order to convert this into RR, what you are going to do, you are going to do one right rotation. Okay, right rotation from where? From this C. Okay, so once you do that right rotation, what will happen? Your tree will be something like this. So see, when you do this right rotation, this B, okay, this element B is going to get pushed up and this C is going to come down, because what you are doing your rotation. Okay, so your tree will look something like this. Are you guys with me till here? Nobody should be having any doubt. I hope I am reaching to everyone. Okay. So again, once this rotation is done, again go and calculate the balance factor. Okay. So at C it is going to be what? 0. At B it is going to be what? 0 minus 1. So at B it is going to be -1. At A it is going to be what? -2. Okay. 0 minus 2. But now we know that this is imbalanced. Still it is imbalanced because it is not within the range. But now what kind of insertion we have? We have insertion of RR type. Okay, we have insertions of right type, and we are very well aware now that if insertions of this kind happens, then we have to rotate on left side. So you pull this median value up. Okay, this median value is pulled up and you have to rotate it on the left side. So once you rotate it on the left side, how will your AVL tree look like? It will look something like this. Okay, so B is pulled up, A moves on the left side because we are rotating on the left side. Okay, and C is on the right of B. So again go and calculate the balance factor. At A you have 0, at C also you have 0, and at B 1 minus 1. So again 0. Okay, this case is clear or any doubt? See, if you have any doubt, kindly do not hesitate. Just ask, okay? If it is clear, it is really nice, very good, all of you. But don't feel that everybody is getting why I am not getting. It's okay. You are studying it for the first time, so fine. Okay, so I hope as no one is raising any questions, so I guess my teaching has reached to all of you. So let's go to the next case. That is your case number 4. Okay. Now your case number 4 is what? Your LR rotation. Okay. Again, I'm going to take an example to explain that case to you. The string given for the elements to be inserted is what? C, A and B. Okay. So again, repeat the same thing. Go and insert C. Calculate the balance factor. What is the balance factor? 0. Next, again go and insert A. Now A is less than C. Okay, so it is going to go on the left side. So C and A. Calculate the balance factor again. So 0 and 1. Okay, 0 here and 1 at C. Balance factors. Again, they are within the range. Nothing to be, no rotation in required. Fine. Next insertion. Next insertion in the line is B. Now B is less than C but greater than A. Okay. So B is less than C. So goes on the left side but it is greater than A. So place that on right of A. Okay. Calculate the balance factor. At B it is 0. At A it is 0 minus 1. So minus 1. And at C it is 2 minus 0. Okay. So it is 2. So I came to know that now this thing needs balancing. It went out of balance. Okay. So see what kind of insertion you have done. Left and then right. Okay. So this case is of what? LR rotation. So in this case, you need to simplify it. Okay. Simplify it to your LL rotation first. Okay. Simplify it into LL kind of rotation. So what you are going to do, from this median value A, you are going to rotate it on the left side because we want to make it as LL kind of problem. Okay, so when you do this left rotation, this A is going to rotate on left side and this B is going to get pulled up. Okay, the B is going to get pulled up. A rotates on the left end. So this is how your tree would look like: C, B and A. Okay, and if you can see, it actually satisfies your binary search tree property also. B is greater than A. Okay, and it is less than C. A is less than both of them, so A is on the extreme left. Okay, again go and calculate the balance factor. So balance factor at A is 0, balance factor at B is 1, balance factor at C is 2. Okay, so again we came across that this is still not balanced. You do need to rebalance again. And what is the case here now? It is your LL case. Okay, LL rotation. So we know that if it is an LL rotation case, then you have to rotate your subtree on the right side in order to balance it. Okay, so when we rotate it on the right side by pulling this median value up, okay, we are pulling this median value up. So this is what you will get as your final AVL tree outcome, where A balance factor is 0, balance factor at C is 0 and balance factor at B. So 1 minus 1, that is 0. Okay, so this is your LR rotation. Doubt anyone? Understood? Any doubt, students? these cases are, important in terms of your MCQs also and in terms of your theory also. Maybe in MCQ they'll ask that if it is an LL rotation, then in which side you are going to rotate to balance your tree. Okay, so it is right rotation. Okay, if it is RR rotation, then on which side you are going to rotate your subtree in order to balance it. So it is on the left side. Okay, in case of LR or RL, again you may get a question such as like, how are you get if it is a 2-mark question, then you might get that how are you going to balance this LR rotation case or RR rotation case or RL rotation case. Okay, so you may give this example and explain your answer if it is a theory question. If it is an MCQ question, then you can remember this mechanism. Okay, see, that's why I've taken only 3 elements, because it is easier to understand with these 3 elements. Fine. So you can remember this mechanism and you can evaluate your answers there. Okay. This is an AVL insert example. Okay, construct an AVL tree. Suppose you are asked to construct an AVL tree. Okay, and this is the given string, that is 63, 9, 19, 27, 18, 108, 99 and 81. Okay, so first of all you are going to consider 63. Okay, so see, 63 is your step 1. Kindly look here, everyone. Okay, oh, it's not seeing, just a minute. 63 is your first element. So go and calculate the balance factor. So 63, balance factor is 0. Okay. Now next in line is what? 9. Okay. So we are also following the properties of your binary search tree. So 9 is less than 63. So go and place it on the left side. So you placed it on left. Go and calculate your balance factors. So balance factor at 9 is 0. Balance factor at 63, 1 minus 0. So it is 1. No need of rotations. Next in line is what? 19. Now 19 is greater than 63, but it is, 19 is less than 63, but it is greater than 9. Okay, so you are going to place it on the right side. Now calculate the balance factor. Balance factor at 19 is what? 0. Balance factor at 9 is what? Minus 1, because 0 minus 1. Okay. Balance factor at 63, that is 2. How 2? This 1 and 2, height of left side. Okay. Minus height of right side. Right side I don't have anything. So 2 minus 0. So balance factor at 63 is 2. Now this went out of range. Okay, so first of all go and see what kind of insertion you made. One was left insertion and another was right insertion. Okay, so this case is of what? LR rotation. And in LR rotation you have to simplify your problem in such a manner that it is LL rotation first. Okay, so if I want to convert this given tree, okay, this given tree into LL type, okay, then I have to rotate from my median value here on the left side. Okay, so when you go and rotate from the left side, you have to rotate from the median value here on the right side. Okay, LL kind. So now you can rebalance it easily. In order to rebalance this, Am I audible? Hello?
Yes, ma'am. Yes, ma'am, you are.
Okay, and my screen is also visible, I suppose?
Yes, ma'am, it is.
Wait. Yeah, even in my other device I cannot see. Okay, visible?
Yes, ma'am, it is visible.
Okay. Fine. So see here it is 63, 19 and 9. Now it is LL kind. Okay. Now in this LL kind, again you are going to rotate on right side because we simplified our problem. Fine. So once you simplified this, what you are going to do, you are going to pull this median value. This median value is what? 19 now. Fine. Now median value 19 is pulled up. So 9 goes on the left side. Okay. 63 rotated on the right side. So it goes on the right of 19. Again go and calculate the balance factor. 0, 0 and 0. Fine. Everyone understood till here? Till step 4? Just a minute. Okay, I hope everyone is with me till the step 4. Now step number 5. After 19, now go and add 27. Okay, where is 27 going to get added? 27 is greater than 19. Okay, so it is going to go on the right side. But it is less than 63. Okay, so it is going to go on the left of 63. So your 27 is here. Okay, so see here 27 at step number 5 here. Left side, second row. So calculate the balance factor. Balance factor at 27, 0. Okay, no issues. Balance factor at 9, again 0. Fine, no issues. Balance factor at 63. So 1 minus 0. Okay, 1 minus 0. So it is 1. Again, no issues. Balance factor at 19. 1 minus 1 and 2. Okay, so 1 minus 2. So it is minus 1. So no rotation required. Fine. Now go and add next element, that is 18. 18 is less than 19 but greater than 9. Okay, so 18 is placed here. Fine. So at 19 again go and calculate the balance factor. Again everything is within the range. Okay, at leaf node I have zeros, at parent node I have minus 1 and 1. Okay, and root node is having value 0. Everything within the range. Okay, so no rotations required. Now next go and add 108. Now when you go and add 108, see here there is one printing mistake. Okay, that's why this I have written 18. I have overwritten this 18 here. Now 108. Okay, 108 is greater than 19, so it is going to be on the right side of 19. Now on the right side 63. Again 108 is greater than 63, so it is going to be placed on the right side of 63. Go and calculate the balance factor. Again everything is within the range. At each and every node you have to calculate the balance factor. Do not forget that. Okay, so 0, 0 everywhere. Okay, minus 1 and 0. Fine. So no need of any rotations. So move to the next element, that is 99. 99 again greater than 19, greater than 63 but less than 108. So it will be placed on this side. Okay, 99 on this side. when you calculate the balance factor, obviously it is going to need the rotation. Okay, because see 99, it is 0, it is 1 here. Okay, then again at 0 0, so no need of rotation till here, because why? Everything is balanced, everything is within the range. Fine, then go for 81. Okay, for 81, 81 is greater than 19, 81 is greater than 63, but 81 is less than 108. Okay, so it is going to be on the left side, but on left side I have 99, so 81 is also less than here 99, so 81 is going to get placed here. Now go and calculate the balance factor. At 81, balance factor is 0. At 99, what will be the new balance factor? 1. At 108, what will be the new balance factor? 2. Okay, so you came to know that here itself the balance factor is going out of range. So if you go for this further calculation, everything will be out of range. Okay, this will be 1, 2 and 3. 3 minus 1. So new balance factor will be what? Minus 2 instead of minus 1. Okay, again 1 and 2, and here 1, 2, 3 and 4. So 2 minus 4. So again new balance factor will be minus 2. So see, everywhere due to this one insertion, everywhere the balance factor changed. Okay, so see here I have highlighted with yellows. Minus 2 here, minus 2 here, 2 here. Okay, and we know that this is the cause. This is the actual cause where you have to, go and rebalance. Now what kind of insertion was it? Left insertion. And the rule for left insertion is what? You are going to rotate your cycle to the right side, selecting your median value. What is your median value? 99. Okay, so you're going to pull this value 99 up. So when you pull that up, look at the step number 10 after your LL rotation. This 99 is going to be the parent node now. Okay, 81 goes on the left side, 108, which was initially your parent node, after rotation on the right side goes on the right of 99. Okay, so it satisfies my BST, binary search tree property. Okay, and also now the balancing factors are within the range. So this is the final construction of AVL tree. This is how you are going to construct your AVL tree. Any doubt here, anyone?
Ma'am, but 81 is greater than 27. Then why can't we keep there?
Because see, insertion, while we were inserting 81, right? What we compared, 81 is greater than 19. 81, so we went on the right side. Right side I have 63. 81 greater than 63, so it is going to go on the right side. Okay, after rotation you are not going to break that chain, the original chain. You are not going to break that you place that 81 here at 27, because then what will happen, that 81 is less than 63, so it does not satisfy my BST. Are you getting? If I place 81 here, that means 81 is less than 63. That's why I went on the left side of 63. But that is not true.
Yes, ma'am, got it.
Okay. Anyone else? Any doubt? Okay. We are going to keep it till here. In the
Ma'am,
yes, Pranjul?
ma'am, before you end up, I just had a simple question. Ma'am, if how we will decide that which number will be in the root, or it will be already
Simple.
given to us?
Just like your BST, the first element will be your root node.
Okay.
Just same as your BST. The first element will be a root node. Rest of all the elements you are going to compare with respect to your root node.
Okay,
Okay.
ma'am. I got it.
Fine.
Yes, ma'am.
So we are going to keep it till here. Okay. In the next session, we are going to see your deletion with an example. Alright. I hope no doubt still here. Fine. BD students, numbers in the chat 1 to 15 in serial order. Okay. D2D students, all 6 of you. Those who are present, write your numbers. But write in a manner D2D AI. Okay. Only 2 of you. Okay. AI students 1 to 10. 11 to 20. 21 to 30. 31 to 40.
Ma'am, my internet isn't working. I think my chat. I'm not able to send messages in chat box. AI 23.
61 to 75. Okay, students, you are free to leave. Thank you all.